Roger, Roger. What's our vector, Victor?
We want to make a distinction between scalars and vectors. So scalars are any quantity that has a magnitude but no direction. Whereas vectors, as we described previously, are quantities that have both a magnitude and a direction. So a standard example of a scalar might be something like mass. So here we have a 50-gram mass, and it's very easy to say the mass is 50 grams, but it doesn't really make any sense to say that mass has any particular direction. It's just a mass. It doesn't have any direction. However, if I were to say, hey, look at that mass, and point to it, the position of the mass would be a vector because the direction would be up from my hand pointing to the mass. So it has a direction. And let's say it's 2 feet away, 2 feet would be the magnitude. It's got some distance, it's got a distance or a magnitude, and it also has a direction. Position can also be given in 2 dimensions, as we discussed previously. So if I say, hey, look at that mass, maybe the mass is 10 feet away, and it's at a 30-degree angle above the horizontal. The horizontal just means the x-axis in this case. It's the horizontal dotted line that you see there in black. And if it's a distance 10 away, I can give the magnitude and the direction by saying it's 10 feet away would be the magnitude, and 30 degrees would be the direction. 30 degrees up from the horizontal would be the direction. But I do also have to give an origin. Much like in one dimension, you always need to define your position relative to some other point. We usually call that point the origin. In this case, the origin is the origin of my coordinate axis, which we've labeled as point O. We've talked before about position and also another quantity related to position called displacement. So displacement tells me how far my object is moved. So if I have an initial position, let's say my initial position is at the origin, and then I move my object to a new position. Let's say again, the object is going to be located 10 feet away at an angle 30 degrees above the horizontal. The displacement would just be the difference between the final position and the initial position. So it's just the change in the distance in the same way, or the change in the position vector, in the same way that it was the change in the position back when we were working with only quantities that were one-dimensional. Now I would like to play a game that I like to call Same or Different. And this is your opportunity to look at 2 different vectors. And if you understand vectors, you should be able to describe whether these vectors are the same or if they're different vectors. So on the left, I have a vector A written in red, and on the right, I have a vector B drawn in blue. So the question for you is, are these vectors the same or are they different? In this case, the vectors are, in fact, the same. They both point up at roughly a 45-degree angle, and they both have about the same length, so they have the same magnitude. So if they have the same length and the same magnitude, these 2 vectors have to be the same. How about these vectors? Well, we can see that they do not point in the same direction. A is up at a 45-degree angle from the x-axis. B points along the x-axis. So these must be different vectors. How about these? Well, we can see that A and B are pointing along the same direction. So that means they're similar vectors. But they are not the same because the magnitudes are different. B is clearly bigger than vector A. Therefore, B cannot be the same as vector A. So these are going to be different. How about these? Well, we can see A and B have the same length. But in this case, even though they seem to be pointing along the same angle, B is pointing in the opposite direction. So these would be different vectors. And in fact, A is going to be the negative of B. So if I take a vector and I multiply it by a negative number, that would mean all of the vector components are pointing in the opposite direction, and I would just get a vector, an arrow that's pointing in the opposite direction. So in this case, we would say vector A equals minus vector B. What about this case? Well, we can see the vectors are about the same size, so their magnitudes are going to be the same, and they both appear to be coming up from the x-axis at a 45-degree angle. However, vector A is pointing a little bit to the right, and we can see it's coming up from the positive x-axis by an angle of 45 degrees. But if I measure the angle between the positive x-axis and B, that's more like 135 degrees. So these vectors are pointing in a different direction. These vectors would be different. How about these? Well, A and B seem to have the same magnitude, and they are both pointing at a 45-degree angle up from the positive x-axis. The only difference appears to be where do the vectors start. So vector A starts at the origin. Vector B starts at a slightly different position from the origin, but both of them are pointing up at a 45-degree angle from the x-axis. Well, a vector is not defined by where it starts. It's just defined by what direction it points. So if A is pointing from a 45-degree angle up from the x-axis, and B is pointing a 45-degree angle up from the x-axis, and they both have the same length, then these two vectors would have to be the same. What about these vectors? Well, we can see the vector on the left is just a simple one arrow vector that we've called A. And the vector on the right looks like a hodgepodge of different vectors. First I go down to the left, and then I go down slightly to the right, then straight to the right in the x direction, back up and to the left, back up to the right, down to the right, and then up to the left. But on net, if I combine all of those different vectors, if first I do go down to the left, and then I go almost straight down, then I go over to the right, etc., I would get a vector that was about the same as A, because the starting point and the ending point, if I look at all of those different vectors and combine them, is going to be the same. What we've done here is add a bunch of different vectors together. This is known as vector addition, and it's a process that we're going to be considering quite a bit throughout the rest of the course. A more practical example of adding vectors, perhaps more practical, is let's say you are giving directions. Let's say you are giving directions from, on this map, Vickner Hall to Olin Hall. And suppose you say, all right, well, go, to get to Olin Hall, you want to go northeast about, let's say 300 meters. And then you take a left and go northwest by 100 meters. That would get you to Olin Hall. Now, there are other ways to complete the same trip. So, for example, you could go northwest first and start at the art building, and then you could go up to the Alfred Nobel Hall of Science by going a little bit north of east. Then you could go due north and go to one of the residency halls. Then you could go at a 45-degree angle south of east, so basically in a south-east direction to the library, and then go pretty much west to Olin Hall. The net result of these two paths are exactly the same. You start at the same place and you end at the same place. Along the red path, you travel a much shorter distance, even though your net, the net distance that you've displaced yourself is the same. The blue path, you get much more tired because you've traveled a much longer distance. But in total, all you're doing is following the green path, going from your starting point to your ending point. Now, what we've been doing here is adding vectors. All we've done to add vectors is I have connected the arrows head to tail. So I took the first red arrow and connected it, its head to the tail of the next red arrow. And I did the same thing with the blue arrows. started at the tail of the first blue arrow and then traveled along to the head of the blue arrow. Then I connected that to the tail of the next arrow. Go to the head of the second arrow, connect it to the tail of the third arrow. Go to the head of the third arrow, connect it to the tail of the fourth arrow, etc., down the line. All we're doing here is what's known as adding vectors together. So to add them, all you're going to do is connect the vectors head to tail and form a path where the arrows tell you which direction you're traveling along the path. Now we want to consider exactly how we add multiple vectors. Right? How do we do this graphically? Suppose I have these two vectors, A and B. Which of the four representations, vector representations on the right, represents the sum of A and B? Is it vector 1 that points up and to the left, vector 2 which points down and to the right, vector 3 which is noticeably larger, which points up and to the right, vector 4 which is about the same size as vector 3 but points up and to the left? Which of these four vectors represents the sum of vectors A and B? Well, it turns out that if I connect vectors A and B head to tail, you should get something that looks like, if we go from the start of B to the tail of A, we should get something that looks like this. Now you might say, isn't that the same thing, or isn't that adding B plus A, not A plus B? If I were adding A to B, shouldn't the A be the first vector that shows up? And in fact, that is correct. But much like adding normal numbers, adding vectors is commutative. So vector A plus B is the same as vectors B plus A, which we can see if I just do this. If I do A first and then B, I get the same thing as doing B first and then A. All of them give you the same result, which is that the correct answer is the vector represented in figure 3. So we can say that vectors A plus B is the same thing as vector B plus vector A, again, because vector addition is commutative. Let's say you're giving directions using vectors. And let's say you want to go from the Carver Hall of Science to the Kent Center. Well, your directions could be, very simply, go north by 150 meters, north 150 meters, then go 200 meters at an angle, at a 30-degree angle north of west. So what that means, bearing in mind, this is north, this is east, this is south, and this is west. We would say at a 30-degree angle, north of west. So I want to go north of west. So from west, we're going to rotate north by 30 degrees, and then I'm pointing at the Kent Center. So those are our two directions. We're going to follow two vectors. One goes 150 meters north. The other goes 200 meters north from west. Well, to figure out how far we've gone on net, we want to look at these vectors, and it's easiest to do this in terms of components. So ultimately what we want to do is we want to look at where did we start, where did we end up, what's the vector from start to finish. So going from here to there is some net vector. We have a word for the vector we get when we combine multiple vectors. This is called the resultant vector. Because it's the result of what we get when we combine these two vectors. Now when I say combine, I'm being very specific here. I should be more specific actually. I'm adding these two vectors. So when we're adding vectors, here's vector 1. I'll highlight this vector. There's vector 1, In blue, there's vector 2. Notice what I've done. I said first I do vector 1. I go up along the blue. I go north. Then I go at an angle to the west. I've connected the vectors from the head of the first one to the tail of the next one. If I'm adding multiple vectors, 2, 3, 4, etc., all you're doing is tracing the arrows, and I say first I do this, then I do that. You follow the path of the arrows, you're just connecting them head to tail. So to add vectors, connect them head to tail. Add vectors, that just means connect them head to tail. What we're going to do next is we're going to add these vectors to get our resultant vector, so we can figure out what's the distance between these 2 points. And not only that, but what's the direction between these 2 points? So what's our magnitude and our direction? Those would be the magnitude and direction of the resultant vector. Let's begin by writing the components of our vector. So I'm going to name each of these vectors. I'm going to call this blue vector, vector A. And I'm going to call this yellow vector, vector B. So we're going to add the vectors A and B together. To start off with, I need to write down the components of vector A and vector B. Well, we said A goes north. I'm going to say, per usual, that X points to the right and Y points up. We're going to say vector A doesn't move left or right at all, so it's going to be going 0 meters in the X direction and 150 meters, positive 150 meters, in the Y direction. Vector A is fairly easy to work out. What about vector B? Well, B moves at an angle. So I have to figure out how far does it move? How far does vector B go in the X direction? And it appears to be moving in the negative X direction, because it's going back to the left, away from the positive X direction. And then it moves up a certain amount too, so it goes up in the positive Y direction. How much does it move? Well, we can figure that out easily enough if we remember our trigonometry. So we have, for vector B, its magnitude and its direction. We want to figure out the components. Recall that the x component of that vector B, actually, let me call it Bx. Let me call this y component By. Remember, we can figure those out from trigonometry, from SOHCAHTOA. Let's see, this is the adjacent side to the angle. This is the opposite side to the angle. 200 meters is the hypotenuse. I can figure out the adjacent side, the value of the adjacent side, using the Ka from SOHCAHTOA. The Ka tells me that the adjacent side divided by the hypotenuse equals the Ka, so that's the cosine of the angle. And from before, we solved that that side would be equal to the hypotenuse, which is 200 meters, times the cosine of that angle, cosine of 30 degrees, which, if you solve for that, will give you, you've got to be careful here. I really want a negative sign here, since we're pointing in the negative direction. So this will actually give you negative 173 meters. So I'm just going to plug that in here. This is going to be negative 173 meters. I'll put the meters in at the end. So I figured out the x component of vector B. Well, what about the y component? me put my x component in first. The x is negative 173 meters. What about By? Well, the y component, as we said before, that's the opposite side of this angle. So if I want to find how big that opposite side is, now we're looking for By. So the opposite side, opposite is O. That would be the SO of the SOHCAHTOA. And it's so it would have to be the sine of the angle. So By, again using our formula from last time, would be the hypotenuse, which is again 200 meters, times the sine of 30 degrees. If you plug in numbers, you will see that this very simply is just 100 meters, because the sine of 30 degrees is 1/2. So this would be 100 meters for vector B. So I've got my components of my two vectors. I say that A goes 0 in the x direction, 150 meters in the y direction. B goes minus 173 meters in the x direction, and 100 meters in the y direction. Well, what's my resultant vector? If I am just concerned with where do I start and where do I finish, what's the net result of my motion? Again, I start here, end here, so I've got a vector going up like this. This vector, this green vector, is A plus B. All I've done is I've added vector A to vector B, and I've got some new vector, let's call it C, which is equal to vector A plus vector B. Now, an important thing to note about vector addition. The length of vector C is not just going to be 150 meters plus 200 meters. It's not going to be 350 meters. Why is that? Well, it would be 350 meters if this vector and this vector were pointing in the same direction. If they both pointed up, I would just connect them head to tail, and I'd get 350 meters distance between the start and the finish. But as B comes down like this, it's pointing at an angle, now all of a sudden C is getting shorter. Okay, so C is going to be smaller than 350 meters. Let's see exactly how big it is. Well, how do we do that? How far has our vector C gone in the x direction? Let's just break C up into components. Well, first, our vector A didn't go any distance in the x direction. It just went straight up in the y direction. Which means the only change in the x direction came from vector B. Vector B went negative 173 meters in the x direction. Therefore, vector C has to go negative 173 meters in the x direction. So this component, the x component of vector C, is minus 173 meters. What about the y component of C? Well, first vector A went up by 150 meters. Then this vector B went up by a certain amount. It went up by an extra 100 meters. So you go 150 meters. Then you go an extra 100 meters. That's a total of 200 meters from start to finish. 250 meters from start to finish. So if I look at the y component, well, by the way, when I look at components, I get rid of the vector hat because a component is a part of a vector, it's not a vector itself. So I'm going to get rid of my hat here to look at the component, which is just the sum of the y components for vectors A and vector B. this would be 250 meters for vector c, the y component of vector c. So I look here and I say vector c has a y component of 250 meters. So this is all we do to add vectors when they're in component form. It's the same thing as adding regular numbers, I just have to do it more than once. If I say a doesn't go any distance in the x direction, but then it goes negative 173 meters, the total would be negative 173 meters. If I say a goes 150 meters in the y direction, and b goes 100 meters in the y direction, the total is just 250 meters in the y direction. All we're doing is just adding the individual components to get the components of the resultant vector. So we've added vector A to vector B to get vector C, our resultant vector. We did that by connecting vectors A and B head to tail, which is how you add vectors graphically. You just connect them head to tail. If I want to add them numerically, what we did is we took all the individual components of A and B and added them together. So I took the x component of A and added it to the x component of B to get the x component of C, which was minus 173 meters. And I took the y component of A plus the y component of B to get the y component of C, which gave me 250 meters. So that gave me the components of vector C. Negative 173 meters on the x direction, 250 meters in the y direction. But now we want to ask one more question. From start to finish, how far have we traveled on net? How far have we traveled on net? Well, that's not necessarily an easy question to answer. The reason being is that we can't just add the magnitudes of A and B. So A was 150 meters, B was 200 meters. Again, I can't just add 150 meters to 200 meters because we've actually gone a shorter distance. We have to use geometry, we have to use trigonometry to figure out how far we've traveled. And once I know the components of C, that's very easy to do because we have the Pythagorean theorem. So if I want to know how big C is, actually, I will write it this way. Sometimes you'll see, if I want to write this as the magnitude of vector C, sometimes you'll see it with an absolute value around it. The absolute value just means magnitude. I also could write it just without the vector hat. And that would also mean just the magnitude of vector C. But using the Pythagorean theorem, we know that a squared plus b squared equals c squared. And in this case, the a and the b are not my vectors a and b, they're the sides. So the sums of the squares of the two sides of a right triangle give you this hypotenuse squared. So we're going to do the same thing here. We're going to take the square root of cx squared plus cy squared, which is going to be the same thing as the square root minus 173 meters squared. Got to square that negative sign to it'll become positive y squared, plus 250 meters squared. And when I do that, let me just get my notes over here. When you do that, you will get a total distance traveled of about 303 meters. So the magnitude of C, I'll put that up here. The magnitude of C is 303 meters. So on net, if you go up 150 meters and then over 200 meters at a 30-degree angle, north from west, on net you will have traveled 303 meters. We could also figure out what direction have you traveled on net. Because remember, it was only a 30-degree angle after you've gone up. a certain amount. We need a new angle over here to figure out what direction we've gone on net. I'm going to call this angle, I'll use the Greek letter phi. But that's easy enough to figure out. We can figure out what that angle is. So remember that the tangent of an angle by SOHCAHTOA, tangent for TOA, TOA would give you the opposite over the adjacent side, opposite over the adjacent side, or equivalently. The opposite side of this angle is the CY. The adjacent side is the CX. I'm going to work with magnitudes here. So we'll say it's the magnitude of CY divided by the magnitude of CX, just to make our lives easier. Otherwise, I'd have to pay attention to that negative sign. So all I'm going to do is say that this is 250 meters divided by 173 meters. Again, to keep things simple, we're going to work with magnitudes, so we'll drop that negative sign. And I can solve this for the angle. So it turns out we can undo that tangent by taking the inverse tangent of 250 meters divided by 173. The meters cancel out because I have meters over meters, so the units go away. It'll be dimensionless, which it should be because this is going to be an angle. And I don't want the argument of the inverse tangent function to have units. It turns out this angle will be about 55.3 degrees. And I can write this angle is 55.3 degrees. And then I have all the information I need. I know my direction given by the angle. We could say that that's 55.3 degrees north from the west direction. I know how far I've gone, 303 meters, and we've also solved for it in component form. So I know how far we've traveled in the x direction and how far we've traveled in the y direction. These are the manipulations that you want to do on vectors using trigonometry. We're going to see this throughout the course, so you definitely want to make sure that you have a good grasp on how to manipulate vectors in this way.